Gauss's law stuff. All right, two infinite parallel sheets are charged. Which graph best represents the plot electric field as a function of x? Okay, so one thing we need to know that when you have the electric field, that this is the electric field inside of two sheets. Remember, the electric field due to an infinite sheet is sigma over 2 epsilon naught. But when we're inside of this thing, well, the pluses are pushing it to the right and the negatives are pulling it to the right. And so we add it together. And so that is the electric field inside. However, when you're talking about over here, it doesn't matter the distance you are away, right? That's what Gauss's law showed us. It doesn't matter the distance you are away from the infinite sheet. The electric field is constant. So in this region, the positives are pushing you left and the negatives are pulling you to the right. And you're like, well, aren't you closer to the positive charges? Well, yes, but we just showed the infinite sheet doesn't matter about distance. So in this region over here, you're being pushed left by the positives, pulled right by the negatives, and they cancel, which is why in this area, the electric field is 0. Same thing over here. Pushed by positive, pulled by negative, totally canceled. The distance doesn't matter. And inside, you do have an electric field, and it's actually exactly that, right? It's from both sheets together. Okay, so don't get tricked by that one. It's actually the easiest answer. Okay. So a lot of these really hard ones, you are going to want to watch the Faraday cage video. A Faraday cage is really tricky. Basically, when you have like an external electric field and you are inside a metal cage, the charges on the cage rearrange themselves to shield you from the external field. Again, I highly suggest watching the electric field or the Faraday cage MIT video, kind of show you an example of what that is. Okay, so in this one, we have a charge placed at the center of an uncharged spherical conducting blah, blah. Okay, so in this case, it's like the opposite. The cage is going to shield the outside. Nothing is going to be changed on the outside, but it is going to be changed on the inside. You are moving the electric field in the inside, so it's certainly going to change, how close it is to certain other points in the interior. But the exterior, that spherical shell, will have charge polarized on it, and it will shield then the outside and make the outside unchanged from what it was to begin with. Okay, electric field outside the surface. Okay, so we know that the charge on a conductor is going to be spread on its surface. And if it's like a sphere, well, then it's going to be evenly distributed. If it's not a sphere, the charge doesn't have to be evenly distributed. The potential, which you probably don't know yet, is actually going to be constant. But we do know the charge will be completely on the exterior, and the electric field is perpendicular to the surface, meaning that the field is going straight out from the surface, right? So if it's a sphere, it's going spherically out. But even if it wasn't a sphere and it was like a cube, and you were looking at the face of the cube, it would be going straight out from that, like normal to that. Okay. A closed surface in the shape of a cube beside A is oriented. Okay, so this one, probably easiest if we demoed in class, because that one's really hard to visualize, but... oh, no, this one's not the hard one. So you just got this cube, right? Whatever field lines go through it to this way, it goes through this way. If the field goes this way, it's going to keep going through. There's not going to be any net flux. All the lines go in, but then all the lines go out. The only way you have a surface, right, where there's field lines that just go out or just go in is if you have a charge enclosed. So if I have a charge inside of this box, like a positive charge, I am going to have net field lines going out. If I have a negative charge in there, I'm going to have net field lines going in. But if I have a box and I have a charge over here, whether it's negative or positive, there are going to be field lines that go boom and boom. Okay, so even though this isn't a constant field, the field is like going this way. Well, I want to always draw an arrow this way through, and it's just going in and it's going out. No net flux. And that's really what Gauss's law says. There can't be any flux unless there's a charge enclosed. Okay, so this one we derived in class, right? This is a sphere of uniform charge density rho. Right, we showed in class that the field grows linear and then falls off like it's a point charge. So right here, the electric field grows linearly until you get to the surface of the sphere, capital R, and then it decays like 1 over r squared like a point charge. And again, you have to be able to derive that. You have to be able to know that it's a linear, and then it's a 1 over r squared. Oh, I don't like this question 28, but it really has to do with the number of like field lines going in and out of something. So if you look at the number of field lines going in to this, there are like 12 negative lines going into this thing and only 4 coming out of this. So this out one must be 3 times the charge. So this has to be a 3Q, and that's got to be a just a plus Q. I don't really like that idea. 8 versus 4. It's really, I think I probably should have wrote 12 versus 4. I'm just kind of comparing, looking at it. But the overall charge, has to be a -2, which means the outer one has to be a -3. So I guess there's just a couple way to look at it, but it really has to do with the number of field lines emanating from a source or going into a source or going into a negative. Has to do with the size of it. All right, the net electric flux. Okay, this is the definition of Gauss's law, right? The net electric flux is 0 if the net charge enclosed is 0. If there's no net charge inside your Gaussian sphere or Gaussian surface, how could there be any net flux? Like I said, if you enclose a positive charge, you're going to have field lines going out. If you enclose a negative charge, you're going to have field lines coming in. If your surface has no net charge inside of it, field lines that come in have to also then go out. So that'd be no net flux. Okay, this comes from the derivation of a uniformly charged sphere, non-conducting, of course. So E, surface area, and then this thing here, this Q r cubed over epsilon, this comes from this guy. Okay, your Gaussian surface has enclosed this much volume. But this is the volume of the total sphere. So then this fraction is the percentage of the total charge you've enclosed. So if you take the percentage of volume you've enclosed and you multiply by the total charge, that then gives you the charge enclosed by your Gaussian surface, which is the red sphere. And we know that Gauss's law says the integral of E dA is the charge enclosed over epsilon naught. And so when you reduce this, you get that answer D. Okay, and that's like the 3rd time they've already asked a question about that. So pretty important. Okay, the point charge shown above here, metal box, isolated, ungrounded, uncharged with the following is true. Okay, so this is a metal one. So this is asking about polarization. So this positive Q is going to draw in a negative Q on the interior of this sphere, and then the outside surface is going to be left with that positive Q, right? So that charge inside that conductor is going to polarize the conductor and create a charge separation. Gauss's law is convenient. Well, remember, Gauss's law is really nice for symmetrical cases. Now, you might think a cube has symmetry, but it doesn't, because we know electric fields are going to go spherically outward. And so when you think about the corner are never going to be the same distance away as like the face, or let's take the center of the face and the corner. And so since the E field isn't constant on your Gaussian surface, it's not useful. Again, the integral only becomes this when you can take the E field out of the integral, and then you're left with integrating dA, which is just summing up all the dAs, which of course is just the surface area. But there's no way you can create a symmetrical or constant electric field on your Gaussian surface with a cube. Okay, what's going on here? A point charge is inside an uncharged conducting sphere. The turn is near electric field at point P inside the shell depends all on. All right, so this is like the Faraday cage principle. This metal thing is going to totally shield the point P from all the external electric fields by allowing the charge distribution to change. The only thing P gets affected by is this interior Q. And again, watch the Faraday cage video again. If the Q wasn't there, would those charges make P have an electric field? And the answer would be no. The cage is going to shield it. So the only thing that does affect it is actually a charge that's inside the Faraday cage. Again, watch that MIT video. It's like 4 minutes long. Kind of gives you an idea how a Faraday cage works. All right, 34. All right, this is again another question asking you about the charge distribution inside a uniform spherically charged sphere. And we already showed you that it is, when you're inside, it grows linearly, and when you're outside, it decays like 1 over r. Obviously, Gauss's law really needs you to learn those things. So when you're looking at Gauss's law, you have to be able to do point charges, metal spheres, insulated spheres, infinite sheets. Surprisingly, there was no question asked about an infinite line of charge or an infinite cylinder of charge. Those, you have to be able to do those as well. I'm a little surprised that, it didn't, but maybe I'm saving that for a test. And I know one of the AP free response questions asked you to look at an infinite cylinder of charge. And so maybe you'll just get more practice there. But you have to be able to do all those Gauss's law examples and then know how it works. Remember, Gauss's law is really looking at finding the electric field due to symmetrical cases. And then there were a few Faraday type principles, in this one as well.